Hi everyone! Today let's talk about Chapter 3, Functions, Sequence, and Relations. Session 3.1, Functions. Let x and y be set. A function f from x to y is a subset of the Cartesian product xy having the property for each x in x set x. There is exactly one y in the set y with the order pair xy is in f. We denote the function f from x to y as f from x to y, okay? So I hope all of you have learned function before. So this session is kind of review of the function we learned before, okay? The set x such that xy in f is called the domain of f. The set y xy in f is called the range of f. So the domain is like the set of inputs, and the range is like the set of outputs. Okay, and then the set y is called the codomain of f. Okay, please notice that the range is a subset of the codomain. For example, if we have f from r real numbers to real numbers, such that f of x equals x squared, and in this case the range is greater or equal to 0, but the codomain, codomain is all real numbers. Okay, so range and codomains, they could be different. Okay, let's continue. Functions can be represented as a set of order pairs, as an equation with words, or as an arrow mapping. Okay, this is an example. F equals the order pair 1a, 2b, 3a. And then we can draw the table here. We have the first circle denotes the set of inputs, and we have the second circle denotes the set of outputs. So the inputs could be 1, 2, 3. The output is A, B, C in this case. Okay, the codomain is A, B, C. And then depending on the F, we know 1 map to A, 2 map to B, and then 3 get mapped to A. Okay, so we can draw the arrows according to the function f. Okay, and this is the first example. Okay, next, you can see here what is the range. So the range here is AB, right? You can see the range is different than the codomain. Okay, so this is another example. Okay, continue. Oh, consider the functions f of x equals x squared. So now we can see, we just mentioned above, right? The function is the set of order pairs x squared. The codomain is r, and the ranges are non-negative. So this is a notation to denote 0 to infinity. So the set of real numbers but non-negative new real numbers. Okay, how about I give you one more example? So f from r to r, let's say f of x equals sine x. What is domain? Well, the domain is r, right? Well, how about codomain? Well, codomain is also r, but how about the range? For the range, we know sine x is oscillating between 1 and -1, so that's the range. So far, so good. Okay, next, modular operators. If x is an integer and y is a positive integer, we can define x mod y as being the remainder when x is divided by y. Okay, for example, what is the following? Okay, 11 more 3, so 11 divided by 3. 3 times 3 is 9. Remainder is 2. So 11 mod 3 equals 2. How about 40 mod 7? So 40 divided by 7. 5 times 7, 35. 5 left. So 40 mod 7 equals 5. That's the remainder. And then 22 mod 4. We have 22, so 5 times 4 is 20. The remainder is 2. So 22 mod 4 is 2. Okay, so because those are the remainders, so you expect your answer is always less than your divisor. Okay. And then how about negative 10? Well, negative, because if it's negative number, you have to be very, very careful. Okay, so negative 10, then you think about negative 10 plus copies of 6, multiple of 6. But we realize 2 times 6 is 12, so minus 10 plus 12 equals, that is 2. Right? So the remainder is 2 in this case. Okay, so minus 10 mod 6 equals 2. Okay. Yeah, so when you have a negative numbers, you want to add the multiple of y such that you get a number. This is between 0 and this number is between 0 and less than y. Okay? Alright, let's continue. What day of the week is 365 days from now? Okay, so let's see. 365. You know how many days in a week? 7, right? So we want to divide it by 7. Well, 5 times 7 is 35, and then 15, so 2, 14, 1 left. So as 1 year, we have 15 weeks and 1 more day. So 365 mod 7 equals 1. Okay, what day is the week is tomorrow? Okay, so let's suppose if today is Tuesday, and then 1 year from now it will be Wednesday. Okay, so it depends on what day of the week is tomorrow. Okay, because I'm pre-making these videos, I don't know when we're get to this. When you watch this videos, what day is in the week of the day of the week is today. Okay, let's continue. One-to-one functions. A function from x to y is one-to-one or injective for every a and b in x. If f of a equals f of b, then a equals b. So here, example of a one-to-one function. Typical example is, what is this guy? X cubed, right? X cubed is one-to-one, and a function is not one-to-one x squared. So this is not one-to-one. Okay, x cubed is one-to-one, and you can see for the parabola, there's 2 points that get mapped to the same value. So it's not one-to-one. Sometimes it's 2-to-1. So it's not a one-to-one function. Okay, so for one-to-one function, we have a horizontal line test. Okay, so horizontal line test. What is it about? So the graph of a one-to-one functions cross horizontal lines at most once. Okay, so the graph of one-to-one function cross every horizontal lines at most once. Oops. Okay. There is also a vertical line test. If you can remember, vertical line test tell us whether the graph is a function. So let me put down here. Okay, let me put it down here. So we have the vertical line test. Okay, so graph of functions only intersect vertical lines. So every vertical lines at most once. Okay, so for example, this guy is a function because it just intersects once, but however, this is not a function because it intersects the vertical line twice. So this is not a function. And this guy is a function. Okay. All right, let's continue. Okay. All right. Examples. Look at an equation and prove that if f from R real numbers to R real numbers and f of n equals 2n plus 1, prove that it is 1 to 1. Okay, look at the definition of 1 to 1 functions. So suppose a and b in the real numbers and f of a equals f of b. What does that mean? Well, f of a is 2a plus 1. F of b is 2b plus 1. Well, we can both sides subtract 1. Then we have 2a equals 2b. Both sides divided by 2. Then we have a equals b. Woo! If we can show a equals to b, then we can say f is 1 to 1. So 1 to 1, sometimes we put this. So 1 to 1. So far, so good, everybody. Okay, next example, if f equals x squared, then it's not 1 to 1. Yeah, we have mentioned it. For example, we can see this point, 1 and minus 1. We have f of 1 equals f of minus 1. They both equals 1. So this is a counter example. Okay, so far so good, everybody. Let's continue. On to functions. A function f from x to y is onto or surjective if the codomain is the same as the range. I.e., for every y in the set y, there exists some x in the set x, such that f of x equals y. Okay, so we can use logical symbol here. For every y, there exists x, such that f of x equals y. Okay, example, show that the function f of x equals 1 over x squared, which is the function of the non-zero reals, to the positive reals, show that this is onto. Okay, so it's very important. Non-zero real, so R non-zero. Okay, to the positive real. Okay, show that the better notation, non-zero real, the better notation is this guy. R, delete the point 0. Okay. So we need to show that for every arbitrary y, where y is a positive real numbers. Okay, so suppose y is any in the codomain, right? Is any real positive real numbers, and we want to find an x, an element of a non-zero reals which maps to it. Okay, so let a be any positive real numbers then a equals 1 over x squared, and we want to find the x. Well, then x squared equals 1 over a. Well, then x is, we can take square roots, and then we get plus or minus square root of a. So actually, we can find two x values to map to the a, and this guy is defined because the a is positive, so square root of a exists, okay, and it's okay to have square root of a in the denominator. Okay, so now we have shown that for every number a positive real numbers, we can find an x. Actually, we find two values of x, such that f of x equals a. So this f is on 2. Okay, let's continue. Show that if a function f of x equals 2x plus 1, where we have the positive integer to positive integer is not on 2. So if we want to show it's not on 2, then we just need to find a counterexample. Okay, we want to find a y value such that there's no x mapped to that y value. Well, think about this. 2x plus 1. So our x is positive integers. So our x is greater or equal to 1, right? So then 2x is greater or equal to 2, and then 2x plus 1 is greater or equal to 3. So you can see this function can only map to numbers that are greater or equal to 3. So now we can pick y equals 1. 1 is a positive integer. Then suppose that f of x is 2x plus 1 equals 1. We want to solve for x. Well, when we solve for x, we get 2x equals 0 and x equal divide both sides by 2, we get x is 0. X is 0 is not a positive integer. Okay? Therefore, we can't find x, which is a positive integer, such that f of x equals 1. So, f is not on 2. Okay? So now we have find the number. So we can find number 1. We can also find the number 2. Okay? You see? This guy is greater or equal to 3. So which means nobody mapped to 1, nobody mapped to 2. So you can also pick the y equals 2 and show there's no x can map to the number 2. So far so good, everybody? Let's continue. Bijective functions. If a function f is both 1 to 1 and on 2, then it is bijective. If a function is bijective, then it has an inverse function. Okay, let f be a bijective function, then f inverse, well, we simply just switch x and y. Okay, we interchange the x and y. For example, if f is 1a, 3b, 6c, determine whether it's bijective and figure out what is f inverse. So let's draw it. So we have the domain is 1, 3, 6. And the range A, B, C, 1 map to B, or 1 map to A, 3 map to B, 6 map to C. You see, one element of X get mapped to one element of Y, and so we can see it's bijective. Okay, and what is F inverse? Well, we just reorder them, right? Then we have A1, B3, C6. Okay, this is the X inverse. We just interchange X and Y. Okay. All right. In general, let me remind you, for inverse function, For inverse function, well, they are images, okay, images across across the line y equals x. Okay, for example, you know exponential function. What is the inverse function of exponential function? The logarithmic function, right? They are inverse function, and this is 1, this is 1. Okay, and let me draw more example here. Okay, so if a function is 1 to 1, we can find its inverse function. So for example, x cubed, we can find its inverse function, this guy, right? Mirror image about the line y equals x. This is cube root of x. This is the inverse function. But if a function that is not 1 to 1, for example, x squared is not 1 to 1, then we can restrict the domain to be such that we have a 1 to 1 piece. So that's why here we can consider these piece. This piece is 1 to 1. And then when we flip it over across the line y equals x, we get square root of x. So even though the function is not 1 to 1, but you can still restrict to a 1 to 1 piece, then you can define an inverse function for it. Okay, let's continue. Composite function. Let g be a function from x to y, and let f be a function from y to z. Then the composite function f with g, composite with g, denotes f composite with g is the function f of g of x. Okay, so this is kind of remind you what you learned in the previous algebra class. Okay, so by the way, if you forgot these and you want to have more exercise, please come to see me. I get tons of exercise for you. Okay. Next, binary operators. A function from x equals x to x is called a binary operators. Okay, and for example, we can define f from R2 to R be f of x y equals x plus y. This is a binary operator. Okay. And another example, the logical operators are binary operators. We have the and or implies. Okay, the x set we have true or false, and then f of x y is like x implies y. Then we can figure out whether it's true or false. We have the truth table. Okay, so this is a function from x Cartesian product with x to x. Okay, for example, okay, if we have true, what's the answer? True implies true is true. True, false. True implies false is false. For true, false implies true is true. False, false. False implies false is true. Okay. All right. Next, unary operators. A function from x to x is called a unary operators on x. For example, we can have f again from x to x, where x is true or false. We can have f of x be the not, okay? The not true is false. Not false is true. So far, so good, everybody? Another example could be we have x is let's see here. Okay, so this is the let U be the universal set. Okay, let X be in the power set. So this guy is the power set of U. That means it's a set of all subsets of U. Then we can define f of x be the complement. Okay, then f of a is a complement, is still a subset of U. So far so good, everybody? Okay, so now you know functions and binary operators, unary operators. They're not only like functions in real numbers, integers. We can also have like logic operations on the propositions, true or false. Or we can have sets. Okay, we can have functions on the set. Okay, so that's it for session 3.1. We will continue in our next class. Have a nice day. Bye.